7 out of 10 serious hacks trace back to one ancient bug: the software. Running your bank, your browser, and your operating system is mostly built in a language called C. C is fast, it's everywhere, and it's about 50 years old. It also happens to be the single biggest source of security holes on the planet. The problem has a name: memory safety. In C, a pointer is just a raw number, an address in memory, with no rules attached. The program trusts that number completely, and that trust is exactly what attackers abuse. Imagine an apartment building where every key is really just a slip of paper with a room number written on it. Nothing checks whether that room is yours or even whether it exists. Write the wrong number, and you walk straight into someone else's apartment. That's a buffer overflow. You ask for room 10, but keep walking into 11, 12, 13, scribbling over whatever's there. Overwrite the right spot, and you can hijack what the program does next. Decades of the worst hacks are basically this one move. People have tried to fix this for years. Rewrite everything in a safe language. There are billions of lines of C nobody's rewriting. Add checks by hand. Humans forget. So the audacious idea behind Fil-C is, what if the pointer itself stopped being just a number? Fil-C takes your ordinary C code and swaps every pointer for something bigger, a fat pointer. Instead of one bare address, it carries the address plus a hidden tag describing what that pointer is actually allowed to touch. Its capability. Think of it as replacing the paper slip with a real keycard. The card doesn't just say a room number, it knows which rooms it can open and gets rejected everywhere else. The door checks the card every single time. So when your code reaches through a pointer, Fil-C first checks the capability. Is this address inside the region this pointer was actually given? In bounds, the access goes through. Out of bounds, the program stops cold instead of quietly corrupting memory. And this is exactly why it matters to you. That check is the difference between an attacker walking past room 10 into your saved passwords and the program slamming the door before they take a single step. The whole overflow trick just stops working. But there's a second, sneakier problem. Sometimes a pointer aims at memory that used to be valid and got freed and reused. Now it points at someone else's data. Tracking who still holds a pointer to what, by hand, is where programmers constantly slip up. Fil-C's answer is a garbage collector for that metadata. It watches every capability and only truly recycles memory once nothing legitimately points to it anymore. No dangling keycard can quietly unlock a room that's been handed to someone else. Put those two together, and you've closed an entire class of bugs at the level of the language runtime itself. Not one patched hole, not one careful programmer, but the whole category of memory corruption, structurally off the table. There's a cost, of course. Fatter pointers and constant checking mean the code runs slower and uses more memory. But for the software guarding your money and your identity, that's often a trade worth making, and it's a trade you can now actually choose. The deeper shift is this. For 50 years, we treated memory safety as the programmer's job, and the programmer kept losing. Fil-C is part of a wave that finally makes it the machine's job. The address was never enough. The point was always the permission.